These events are crazy. I love them though. Man, you guys are like really quiet. It's like your head going wong, wong, wong. You guys about ready to get started? Okay. Okay, so let's go ahead and get started. So my name is Daryl Hyland. I'm the research lead for IoT technology at Rapid7. So I'll be bouncing around here quite a bit. So this presentation, so the device we're actually going to show in this presentation, it's not a negative against the producer of this device. It was just an example that we used. So I actually liked the device. I thought it was, at least the iteration of this model that I looked at, I thought was fairly decent security. But so I just wanted to point out, so as if you identify who the vendor is, don't go, oh, this vendor has a problem. In my book, I didn't see any problems when I looked at it. At least nothing that was anything critical. That doesn't mean someone couldn't find something if they wanted to dig deeper into firmware or something like that. But that wasn't the goal of this. The goal of that led to this presentation was, you know, as hardware hackers, we're often doing things with what's known as like deconstruction. So we're pulling chips, things like that, and often we rarely actually put the devices back together. So in this case here, I was like really getting tired of that. So the goal was, well, let's learn how to actually put them back together. But in the same process, when we're in those situations where we want to get some level of root access, and even though we get like password hashes off the device, we still can't get root access because either the hash is something weird, like in this case, when we pulled the hash off the device, the password hash for root, it looked like a standard old style DES, but it would not crack, even in the biggest cracking machines we could run it through. So I'm not sure what they did to it or what it really was, but we weren't able to crack it. So that brings us to two rules that I came up with as a hardware hacker. Always want to gain root access, right? I mean, it's kind of fun. If we get root access to the device, it opens up another area of further testing on the technology. So now we can do various in-memory testing on the device, which is always a positive goal. And the second thing, always return the device to full operational condition. Of course, in this particular project, I have more dead boards than I have working boards because I destroyed a lot of them in this process. But I learned a lot during this thing, and I want to share that with you today. So what we're going to talk about is opening the devices. Often when I'm talking to people that are just wanting to get into hardware hacking, they're like, what are all the tools that you should buy? And I'm like, let's start off not buying any tools. Let's start off just understanding how to open a box up and how to examine it, how to identify components on the boards, things like that, pull down data sheets, try to figure out what the hell it's actually doing and how all the components interact from a visual and a technical aspect using data sheets. Once you get to that point, then you can actually start understanding the boards. Let's go to the next phase and maybe look at picking up a couple tools. Then we're going to talk about examining the PCB, removing memory chips, and if you've done any hardware hacking, this is a common technique. Pull the chips, pull the memory. Extracting data, firmware, file systems, that type of stuff. Then I wanted to get into modifying the file system. So what if I pull the firmware off the device and I can't crack the root password? What can I do next from there? Can I actually change the root password? Can I add new accounts to the firmware? Can we put it back onto the board? All that type of stuff. We're going to get into restoring and modifying the file system of the chip and then restore the chip to the printed circuit board. This is fairly simple if you're dealing with standard SOIC chips that are gull-winged that you can solder. But what about BGA chips? The ones where all the connections are underneath the chip. How are we going to do that? So we're going to cover that today. And of course, we're going to do root. Now I have videos that I've done for all the different segments as I work through this, and we'll run those through and we'll talk about what I did, why I did it, that type of thing. So the first thing is examination of the board. So we open up this board, we start looking at all the components. We can find the CPU, we can find the RAM chip. The cool thing with the RAM chip, and I point out to people, I don't know if you can see it in here, but often the quickest way to identify the RAM chip without even looking at the data on there is look at all these weird squiggly lines that lead to the chip. Often the chip communicates in parallel. These are kind of like delay lines to make sure they're all in sync with each other, so parallel transmission of the data within the chip. And of course, this is a home IoT hub, so it has a lot of RF communication functionality. It has Zigbee, it has Bluetooth Low Energy, it has Z-Wave. Also, we want to gain some level of access to the board, and I always try to find out, hey, does it have UART? Often when we have devices that have full board operating systems on board, embedded Linux operating systems, we can usually find a UART, and hopefully it's activated and hasn't been disabled in some weird fashion, either programmatically or cutting runs or removing the load resistors or things like that to prevent access. So often when you find these, there's not going to be a header on there. So it's just going to be pin or holes. So you solder up and you connect to it and try to identify it. And that's generally what we're going to do. In the case here, the tool I like to use is a Shikra. Anyone else use the Shikras? It's a standard FTDDI serial interface. It also does JTAG. You can do SPI with it. I think it's like $45, $55. It's fairly inexpensive. I like this much better than like the Bus Pirate. It's faster. It actually works when I try to use it versus fighting the Bus Pirate a lot of times. And so we connect up to that terminal once we identify it. Often when I go to identify UART, there's a number of tools. Like JTagulator has the ability to identify the UART pinouts. I find it easier just to use something like a logic analyzer, like a Sele logic analyzer. Hook it up with all the pins, try to see what's communicating on them, and then see if we can identify the data lines, the transmit, the receives, and decode it with a logic analyzer, identify is it a UART, and figure out what the pinout is. So in this case, we connected up to the device with the Shikra using a standard screen terminal program. We can connect to the Shikra via its USB connection, and we can watch the device boot up. And most common, we get up and we get a root or a logon for the device. In this case, we don't know the root password. So the adventure starts. How do we get this root password? So the next thing we want to look at is where is the actual flash? Where is the firmware actually stored on this device? So we come to what's known as an embedded multimedia controller. This is a BGA chip. So we can't tap into the leads on it. We don't even know where they go. So we have to be able to examine this somehow. And this particular chip, when we try to pull up a data sheet, I actually couldn't find the Micron JW999, but I did find somebody had a cross-reference that said this chip actually equates to this particular Micron chip, which is basically a 2 gig chip. It's a 153 ball BGA 2 gig chip. So now that we've identified it, how do we go about reading this chip? The one way that I always like to read chips is the destructive method. Reading chips in circuit can sometimes be a challenge, but when you pull them off, it's way much easier. So then we get into the process, how do we go about pulling chips off an actual board, especially BGAs? We could use a hot air reflow. This is an inexpensive hot air reflow. I purchased this on Amazon. I think I paid like $9,500 for it. These work really well. They're inexpensive, they're cheap, but also be aware there's been known issues with these, so I would not leave it plugged in. They've had a history of like spontaneously bursting into a ball of fire. So take that into consideration when you leave it plugged in. I actually have my hot air bench on a power strip that's left turned off all the time because most of my stuff is weird Chinese cheap shit knockoff. So I prefer my lab not to burst into a ball of fire. So we quickly hook up the hot air reflow in this example, and I've actually used this thermal tape around it to protect other components. Now solder that's used, if the solder balls on these is the common 6337 metallic composition, the temperature they melt at is about 361 degrees, or I believe 183 degrees Celsius. Also be aware, if you're buying Chinese stuff, you will quickly learn Celsius, because a number of my devices don't do Fahrenheit. So in this case here, we hook up, we do the hot air reflow. Get it here, new presenter, hot air reflow, and we are actually able to pull the chip, which we show in the right-hand corner. From there, you can put a little solder paste or solder flex on it and go ahead and clean it off with some solder wick and clean the chip off. And that way you can actually read the chip. And we're going to talk about how we read those chips here in a minute. The other way for pulling it, this is something I went out and bought a little later on when I got ready to do more reballing type work, is an oven. This is all done in Celsius. This is oven's like $185. So if you don't have $185, go to some yard sale, buy some cheap-ass toaster oven and modify it. There's more than enough information via Google and YouTube to be able to modify it. But if you're like me and you like things that's a little more push button, easy, less likely to burn my house down, well, probably not this one then. But this has like 8 settings on it. So there's 6 fixed settings. So in this case here, you can control the thermal rise and thermal drop on the chip, which is much better for preventing damage to the chip so you don't create thermal shock. I don't necessarily think you're going to get that good of control with a toaster oven, so you may be a little more thinking about that as you're working through that process. But this one works pretty good. So here's a video. So I run it through, it's at the top cycle, I pull the door open, I use a suction tool, and I lift the chip right off. This is sweet. It's easy, it's simple, but you got to be aware. At this point, every component on that board is loose. So if you yank the door open hard, bad things may happen. Now, often with chips, when they, because when I first started doing this, I'm thinking, damn, an oven, what about all the chips on the bottom? Are they all just going to freaking fall off? The answer is no. There's this cohesion factor with the solder that will actually suck them up to the board to keep them from falling off. So once the chip's loose, the solder's melted, you can actually tap it and watch the chip wiggle and line itself back up on the pad. It's kind of fascinating to watch. I was doing an engagement for a customer, and the device they had was a small Android-based board. It had Android on it, small, and I wanted to remove the chip, and they had actually used epoxy, and epoxy the embedded multimedia controller on there. So I went in and I ground around the edge of the multimedia controller so I can get a spudge up underneath there, a metal spudge, which is a small flat metal piece. Ran it through the oven and I pulled it out and had a glove. And I was able to get the chip off, but in the process, I flung freaking components all over my lab. There was chips all over this place, capacitors, resistors. So I swept them all up and shipped them back to the manufacturer in a plastic bag. So here's your device, probably ain't gonna work anymore. But I was able to get the embedded multimedia controller chip off and was able to pull the data off the chip and analyze it. So now we've got to the point where we've either through hot air reflow or through an IR oven, we have the chip off of it. And like I said, you can use solder flux and some solder braid and clean the chip up. And then you want to be able to pull the data off this chip. And what I use is, there's a number of things to do, but I use these devices here. These are about 135 bucks a piece, and they come in various BGA sizes. I'll pass this around so you can see it. So the lid opens up, and you'll see us actually use it here in a second. You put the chip on there, you close the lid, it's USB, plug it in, 135 bucks. There's some cheap Chinese ones that are SD card type things you can plug in, or you can go out and build your own, okay? So there's a number of instructions online on how to build these devices. To some extent to be able to do that. I'm not wanting to build shit like that. I want to do work. So I just spent my own money, went out and bought these. I'll pass this around so you can see it, get a closer look at it. I ask that you try not to open and close this too many times because it has a life cycle. And if you do, try not to break it off. So we can pass that around so you can look at it. And the cool thing with embedded multimedia controllers, and I've talked about that I think last year here also, is Everybody in this room, if you have a cell phone, you have an embedded multimedia controller on you. Every one of the cell phones has these chips. And these chips are really cool because they will actually mount up just like a file system, a hard drive. So we're going to take this, we're going to install it in here, and you're going to see this mount up here in a second. Plug it in USB, hit the button, it connects up. Lights should start flashing here in a second. And we'll quickly see that it mounts up an entire file system, easily giving you access to all the data. Now these file systems will typically mount up, but not all the time, but typically will mount up as read-only file systems, so you can't alter them. There's been a couple cases where you can actually unmount the file system using standard Linux tools and remount it as read and write. Almost every time I've had that successfully work, it was an Android-based operating system. I don't know why, but that happened to be the case. In this particular case, this thing was read-only. I could not remount it as writable. So now how do I get the data off of it? How do we go to the next level? How do we modify this data? I can see the file system, but I can't modify it. But if we look up here, this actually mounted up as various partitions, just like a hard drive. So we should be able to gain access to the individual partitions. This makes it much nicer than trying to alter the firmware out of a blob. Pull an entire firmware block off and then try to break it out, clean it up, make changes to it, put it back together and make it functional, which has its own problems. This is much easier because we can actually pull the individual partitions for alteration. And again, with this, it's fairly easy, standard Linux commands. We can actually pull the partitions using DD, like we would with any hard drive. So yeah, so I'm looking at the file system on this device, and you can see it has multiple partitions, as I mentioned. The interesting thing on here, the partitions of interest on this one that are actually the real file system is 3 and 6. There's 2 identical partitions on there. The reason why there's 2 identical partitions is for upgradability of the device. Anytime you want to do an upgrade to an IoT-based embedded operating system device, there'll be 2 partitions. When you download and install the new firmware updates, what it'll do is it'll write to the offline partition. That's defined typically in the environment variables on the U-boot or secure boot. It'll tell which one is primary, which one is the offline one. It'll write the offline one, and it'll do it with DD. Every one of these operating systems have DD in it, so it'll rewrite the offline partition with DD, and then it'll go through a reboot cycle. It'll change through the environment variables, which is the primary, and it'll bring up the new version. The reason for that is if your firmware goes to hell in a handbasket during an upgrade, you don't brick the device. If there's only one partition, one operating system partition, you could destroy it during the firmware upgrade. This prevents it because if it fails during boot, it'll reboot itself, change, and come back up on the primary one again, which hasn't been altered yet. And in this case here, I think that video actually just went through and, did I do a DD on that? I can't remember. Okay, so it went through a DD, it pulled out the system, and it did an unsquash on the system. So we go through an unsquash of the file system, and that way we have data that we can actually modify. It's no longer read-only data. We did a DD, we got the binary, we did an unsquash of that partition. In this case, it was, I believe, 6. We went ahead, unsquashed it. Now we have the entire file system that is writable on our hard drive, and now we can modify it. In the case with this particular project, the goal was to just change passwords. I didn't want to do anything else weird or strange at this point. Just wanted to get root level access. So I modified 3 files. I modified the password file, the shadow file, and the group file. I created the new user. In this case, I called the new user Bubba. So Bubba, and then I changed the root password and gave Bubba a password, and the password happened to be test1234 is what I actually used, a real highly secure one. And then from there, now that we've had this changed on the system, the goal is you want to re-squash the file system. So we go back through and we do a make squash. So real quick here, we'll walk through this. We'll step back to the directory, so we're not in the directory we're actually modifying. And we'll go through with a make squash operation to turn this back into a binary file that we could DD back onto the actual device. A couple commands here, no pin, always use fragments. These commands basically make it possible to ensure that we best utilize the block sizes of the data so that they're not spread across. If we end up writing a single file to a single block, you're quickly going to eat up more space than you can actually get back onto the actual chip. Using those commands makes it possible to compact it up properly so we have a good structured file system into the binary, giving us the ability to actually fit it back on the chip. Now, of course, with DD, you can make a lot of different changes, and you can actually set block sizes and all kinds of other settings. In this case, I didn't have to do that. If you were dealing with something weird, where they were doing weird block sizes that would chip that was weird in structure, you may have to consider those type of things, but in this case, I did not have to do that. And again, once we have this back into the binary, the goal is to put it back on the device. So we created the binary called squash, alt P6, the altered file system for P6. In this particular case, when I did this, I got brave and I actually wrote both partition 3 and both partition 6. So it was one of those things, either it's going to work or it's going to go to hell real quick and basically make the device totally bricked at that point. And we did run into some problems, and we'll talk about that here in a few minutes. I really type slow, that's obvious. Well, it's better than watching me doing up on stage. That gets kind of freaky. Watch how I can spell DD wrong half a dozen times. So here we're actually able to write it back to the chip. So now we've successfully pulled the chip, pulled the memory, unsquashed it, modified it, re-squashed it, DD'd it back to the chip. Now we have a chip. So now what the hell do we do? This is where the adventure started. Up to this point, this is very common, very easy stuff to do, easy to understand. So getting into the reassembly of these components. This is where I had no freaking clue where I was going or even if I could actually do this. I've seen people do it on YouTube videos, and I always sat back going, oh, what the hell? I don't think I could do that. So we're going to reball it, and there's a number of ways of doing it. You can use a screen kit. So here is a screen kit, and the way this thing works is you mount the chip in here, like it's showing in the picture up there, and you purchase a screen. Now these chips are 153 ball BGAs, and they're like extremely small as hell. And I'll start with pass a couple of these chips around. I don't think either one of these are any good. I think one of them's good. I'll pass these around so you can see the size of these chips. Now when you look at these chips, there's actually 153 balls on these chips. So I had a hell of a time finding a screen, but I eventually tracked one down through some site in China. It took me like 45 days to get it. And I don't know if you can't see it, it's really freaking small. We ran into a problem. The pad size on these chips is actually 0.3 millimeters. So you can use 0.3 balls or 0.25 balls. The screens are all cut at 0.25 millimeters for balls. The problem is it's thicker than 0.25 millimeters. I had a guy track, when I was over in Paris here earlier this year, we had a guy track down a manufacturer because we were talking about this, and I was bitching about them being too thick. And he could only find somebody that was willing to cut these for us at 0.35 millimeters. So if I'm putting 0.25 millimeter balls in here, and these balls are like freaking specks of dust, and yeah, we'll pass that around too. So I always like it. It's like I told somebody, presenting at a conference is like being in second grade show and tell. It's fun as hell. It's where I got started at. So I'll pass these around. One of them is the 0.25, one is the 0.3 size BGA balls. And these containers, right now, I think there's probably maybe 10,000 balls in each one of these. So when I started doing these, And we'll show a video here in a minute actually going through the process. I've probably used maybe 2,000 of these balls. There's 25,000 balls in these things. I say based on the amount that are in there, it's about 10,000 left, and I've used 2,000. So somewhere in my room, there's 13,000 freaking balls. And I have no idea where the hell they are. Now, if you open those up and spill them, you need to pick them up and count them for me. So there's 10,000 in there. And here's the screen grid. So you can see that. So since the screen grid's too thick, and you can literally have at least if you're doing 0.25 millimeter balls, you still have 0.1 millimeters of space there for a damn ball to get jammed into. So using the screen grid, it took me about an hour and a half to get this shit straight and then reball a chip. And I'm like, this sucks. This sucks so bad. So what do I do? How do I go about doing this? So I thought about it, and I thought, oh, what the hell? Let's just do it manually. So I have an actual microscope, and the goal is we're just going to manually reball these. So it's really easy. I'm sorry, it is easy. Don't sit there and go, hell, I couldn't do that. Now, if you have a medical condition where that you tremble really bad, you're probably going to have a problem. You probably have a problem with the reballer kit also. But if you don't, even if you have a small tremble, I'm well into my 50s. I'm in my mid-50s. I'm not 20-something anymore, and I have a typical tremble as you get older. There's ways to stabilize your hands. Often the way to stabilize yourself during soldering or this type of method is a weight. So if you put your hand over your right hand, if you happen to be right-handed, and put pressure down, you can completely bring your hand to a full stability so that you can actually do this. I have tweezers that are actually sharp enough to go clear through the skin. I tracked those down on Amazon. They were like 20 bucks for a pair of those. And it makes it possible to do this. So manual by hand's easy. You need patience. Unless you have really good freaking eyesight. Now, I have to admit, when I was in my early 20s, I could have probably done this without a microscope. That's how good my eyesight was. I remember a worker I had, because I was bragging about how good my eyesight was when I first got out of the Navy and was working with this guy, and he thought he'd be a smartass. He hands me this little die, and the top of it is 1/8 of an inch. And he goes, what's engraved in the 1/8 of an inch? And it was the Lord's Prayer, and I looked at it and I read it to him. The guy about freaked out. Now, at 56 years old, it's amazing I can actually see my hand in front of my face. So in this case here, I actually use a microscope. There's a number of different microscopes. There's a couple X10, X20 magnification type microscopes that work pretty good, and you could probably use them to do this fairly easy. Mine happens to go X3 up to X90. It's a little more expensive, but a decent microscope to be able to do this can be purchased for less than $200. So in that case, it's still very doable. Now, of course, everyone goes, this is crazy, Daryl. Do you really do that? Well, I got to have a video. So I cut this video on Sunday. So you start off by actually fluxing it. The interesting thing is when you're putting the flux down on this, you got to make sure it is very thin. If it's too thick, the balls are so small that when the temperature comes up in the oven, it'll actually cause the flux to boil, and the balls will float up on the boiling flux and will merge together in big blobs. Trust me, I've done that a couple times in the learning process. So this particular tweezers, the point of it, that is size of actually a sewing needle, the tip of that, to give you an idea of the magnification. So we can kind of whirl through this. I probably don't want to spend all of my time watching this crazy video. We can speed this up a little bit, and you get to see my thumb. Let's see if we can jump forward a little bit. Getting a little closer. Now, how much time does it take to actually do this? There we go. Hey, I didn't get any further, did I? So how would the screen have worked? You lift it off after placing it? Yeah, the way the screen works is if you have the device that's going around, has the two handles on the side. You mount the chip in there, you put the screen grid over top of it, you flex it, you put the screen grid over top of it, you pour the balls in, you fill all the holes, and you take those two handles and you pull them down. And that'll drop the chip down below it, and then you take the grid off. And then you can raise it back up. From there you can take it out. Now you're thinking how, the balls, how do you get these balls in place? How do you deal with them not rolling off? The magic is the flux. They stick to the surface. The one thing you do have to watch out for is if you start getting flux built up on your tweezers, the balls will start sticking in. You'll be like trying to fling the shit off. They don't come off very easy. Remember, they're like 0.25 millimeters, so they're really small specks of dust. Oh, kind of finally jumped up there. So we'll let this kind of run through. So these pads, like I said, are 0.3 millimeters. In this case here, I'm thinking I'm balling it with 0.3. But typically this would be done, from what I read on this particular chip, 0.25. But either one of them will work for the process. So one of the things you want to ensure that the balls are on the pads and that they don't have to be in the exact center of the pad. So they could be toward the edge, because remember, when it melts with the flux, it's all going to line up on the pads. The one thing you want to avoid is balls that are all the way to the edge of the pad and two pads close together. So once this is all done, you see I go through and I go through a physical lineup. Any ones that are too close to another ball, I kind of modify them over. This whole process takes, now we kind of sped this up, as you can see. It took about 20 minutes to reball this. So what I typically do is I go through, and there you can see, we got all the balls on there, close enough on the pads. They're not too close to each other, so we're not going to run into any issues. Even like that one, it's still on the pad, it's on the edge. It'll line up when it actually melts. So that'll work pretty good. And it's doable. And when you're moving it around, remember there's flux on there, the balls are going to stick. Short of dropping it or flinging it or doing something, they all should stay in place. There's a number of different fluxes, but it's actually specifically made for reballing. It's a thicker paste that you use. This is a Amtech brand, but there's a number of different brands. This one worked, so I kind of stuck with it. And I mean, it's like a big freaking bottle, this shit, so it's going to last me a while. No, this is not lead-free solder. I don't like lead-free solder. It has some of its own issues. These balls are 6337 combination. They melt at 183 degrees Celsius, which is 361 degrees. So, and that's the temperatures they actually melt at, which is going to play a big part in the next phase. And that is actually reflowing these. This is where I ran into some problems. So when I used the IR oven to actually remove the chip, I actually used a temperature of, and you'll have to do your own conversion, 250 degrees Celsius. So I've gotten real common and have figured out Celsius and sticking with it. But 250 degrees Celsius, which is much higher than the melting point, since the melting point is 183 degrees. And the reason for that is the board consumes a lot of heat. We run into the same problem when we're doing hot air. So you can put hot air on it, you think, I put a 400 degrees and I'm pointing it at the chip, it should melt. No, it will dissipate so much of the heat. So you have to find those right temperatures, like with the hot air, and you bring it up to pull the chip off, you do it slowly. And then at a certain point, I found that easier on the hot air for removing the chip, so I'd like to cover that real quick, is to raise the temperature up really high. And then keep tapping the chip until it comes loose, then remove it, because you want to do it quickly at those high temperatures. You could potentially damage the chip. So in this case here, I used a temperature of 250 to originally pull the chip off the board. So when it hit the top peak, I was able to open the drawer, pull the chip out, and then let it cool back down. But when you get ready to actually refrow the chips, you're not dealing with the entire temperature of the board dissipating the heat. So I took the chip, I put it in the oven, I left it at 250 because hell, 250 worked for pulling it off, it should work for reflowing. So we run into a little problem here. So you notice the chip on the left is green, you notice the one on the right is brown, brown's bad. I actually totally toasted the chip. I mean, it didn't work anymore. It was cooked. So I'm like, okay, the reballing went really well, but you know, if the reball works and the chip looks like a brownie, the project failed. So at that point, I had a couple dilemmas. One was, I only had the one damn board. So I'm like, shit, dead in the water. Can I buy new chips? No, they're OEM'd. So it was like, oh, what the hell do I do? I'm like, this board was $75 for this device. So I'm like, oh, shit. So I head down to the store. I'm like, I'm going to have to ante out $75. I want to get this project done. And I go in there. They were 50% off sale. So I grabbed a whole bunch of them. I figure if I fail once, there's a chance failure could follow me. So I went ahead and spent the money and bought like 3 more of these devices so I'd have them. So I went back and said, okay, what's the correct temperature? So at about 220, 225 degrees Celsius, I think that's right around that temperature, it turns out that these boards are made of a fiberglass substrate. At that temperature, the fiberglass substrate begins to break down, okay? So that's a bad temperature. This chip's small, so it's going to heat up quickly. So I said, what should I pick a temperature at? So I came in right around, and of course the ovens are not perfect accurately. So I came in with my oven and I set it at around 205, and I set a very short peak temperature. So it would peak and not stay there long at 205. And would add, reballed another chip manually, another 20, 30 minutes. You know, I do like 3 lines manually, take a 5-minute break, same thing. Don't drink coffee. That gets really bad. Then it's like an hour and a half. And you're like, oh, damn. But went ahead and did that. And I put it back in the oven at 205 degrees, ran that through. This time, it did not burn the chip out, but this is where I screwed up with the flux, and I had too much flux. So when I pulled the chip out, unfortunately, I don't have a picture of it. 2 of the corners had big blobs of solder where it all consumed together. Cleaned it all off. The chip was good. I put it back in my chip reader to make sure that 205 did not fry it. It was good. Went ahead and went through the process again, reballing it, less flux. And we came out, this happens to be the one when I cut the video that you seen a minute ago. This happens to be the chip that I did the reflow on, so we could see that. It still has a little bit of flux around the balls that are kind of dark. Of course, this was a damaged chip, as you can see. It's not even brown anymore, it's black. But went through that process. The reball went good, so now it's put it back on the board. So how do we get it back on the board? Again, you clean the board off. If we look at these chips, we'll see this extra pin here and a marker up here. That's for lineup, so you can identify where basically the pin 1 location is. The boards will have an outline on them, a white outline around where that chip and a marker where that corner should be on that. Again, you clean the board, good. Clean it with alcohol, and then you come back up, or there's other chemicals you use besides alcohol. There's a big back and forth on what's good to use. Some people like to use this other chemical, I don't remember what it is, for cleaning flux off and cleaning the debris off a board. I just use alcohol, but be aware alcohol can actually create a film also. So I often, once I clean it with alcohol, I take a lint-free cloth and kind of buff that film off there. So consider that. And then I went ahead and lined it up. Okay, I lined it all up, I fluxed it, lined it all up. Too much flux is probably not a horrible thing in this case. I don't know what that would do. I put enough on there, I thought the surface was covered fairly even. Lined the chip up, fed it back into the oven. This time I went back to the 250 degrees. And then before I hit the button, I go, oh shit, stop, wait a second. What do we need to consider? Well, we have to consider that these boards, when you're cooking them, and I'd considered it, when I pulled the original chip, I'd pulled it with originally hot air. Okay, the first one I pulled that I did it with. And I was putting it back on the same board that I did the hot air originally pulling the chip. So that board had not been in the oven, and I hadn't put a whole board in the oven yet. There's plastic components on these boards. So if you put it in the oven, shit melts, okay? Which is not always a good thing, because you're like, success, oh shit. But I realized that up front, I realized that. So I had the bad board that I originally screwed up, and I'm like, let's do an experiment. I don't want to have to pull all these components. You know, I don't want to have to pull the USBs off. I don't want to have to pull the Ethernets off. I don't want to have to pull all these push buttons off. Well, let's find out what the hell melts at 250 degrees Celsius. So can't really see it here, but if you look close, you can pass that one around, you can see the components that melted. So the speaker melted and the power jack melted. Okay, so now I know. So I took the board that I was going to rebuild properly, and I went ahead and I pulled those components off. I just desoldered them. Put the board into the oven, ran it through the reflow process at 250 degrees. The bell rings, bing, you're like, oh, I wonder if it's going to work. So also remember, I rewrote both file systems. Partition 3, partition 6. One of those, I didn't know what the primary was because I never looked at the U-boot environment variables. I wasn't able to get to those. So I didn't know what was the primary, and I didn't want to have to do this twice, so I went ahead and rewrote both of them. So I either screwed both of them up and it all fails, I screwed one of them up and it works, I screwed neither of them up and it works. So I went ahead and ran it through the board, ran it through, oh gosh, dang, man. Okay. So you throw me off stage now? Okay. We don't, that's just me actually doing root. So we can come over here. So you can vaguely see. It doesn't matter. All it is showing me log in with root on this device to get root access. There we go. So we come in with root access, and this is after total success. So I log in with Bubba. I didn't create a directory, so I got a bunch of directory errors. Okay, oh, I didn't think about that. Okay. So then I go ahead and go SU. I log in with 1, 2, 3, 4. And the good thing is I created an account on the box because I did find out or did think up front that root could not log on at the boot up at UART. They were not allowed to log on as root. So luckily I created 2 accounts. The interesting thing is when I looked at the file system early on when I pulled it off, it told me that root could log on. Once I got to this point, somewhere it overwrote those files that controlled that. I'm not sure where that came from. But here I was able to log in with root on this particular device and gain access. What did happen during the initial boot up? I initially powered the thing up. Of course, I didn't record it at that time because I was just doing some research. It was a shit storm of errors. Just error after error, file system errors, fragment errors, just all kinds of shitload errors. And then the thing went down, boom, rebooted. I'm like, well, so much for that shit show. So then it comes back up, starts generating a shitload of errors second time, and it's only half as many errors. Boom, it reboots again. Third time it came up. Well, the fourth time it came up completely clean. So what happened? I'm not 100% sure. There's a couple things that possibly happened. One is one of the partitions that I rewrote was totally corrupted and it was the primary. And it tried rebooting on that several times and then failed over to the secondary and switched over through the environment variables on the secondary and came up that way. I'm not sure, but either way, it came up. I had root access. At that point, we're able to do a number of things, a number of testing. So we're not going to go into any of that testing because this is about this whole process of learning how to actually reball BGAs with the ultimate goal of encouraging everyone to go out there. And if you like doing this stuff, let's not stop at just breaking the boards. Let's look at how we can, instead of your lab being a pile of shit, screwed up boards, which I have many, let's go ahead and learn these processes so we can put these boards back into service. Now, hopefully we can get those lights off because I have a few more minutes and I would like to quickly cover something. Now, you can actually do mounting of embedded multimedia controllers while they're actually on the board. It's possible. It turns out to control a embedded multimedia controller, there's 5 connections you have to maintain besides ground. You have a command line, a clock line, a data line, VCC, which is system voltage, is normally 3.3 volts. And then you have what's VCCQ, which is the controller voltage on the chip, embedded multimedia board. Because it has its own controller, like a drive would, okay? It's a different voltage. It's usually 1.8 to 2.8 in voltage. So you have the ability that you can actually take a chip off and do what's dead bug and connect all of those connections with the right kind of device and be able to mount the chip up with not having to have one of these components of mine. Or you can literally do it in circuit. The way to do it in circuit, and if people want to catch me after this presentation, I'll actually have a device set up, one of the exact devices, where I'll show mounting up the chip while it's still on the IoT device on my system. So here's the connectors on the board. Now, the only way to find these connectors is via X-ray in the machine, possibly, or go ahead and pull the chips. You can pull the chips, you can chase out all of these control points. To be able to do it on board, you don't need to worry about VCC and VCCQ. Those are supplied by the IoT device's power supply, and you can bring up the board. So what you do is you tap into these with a device. You can build a device. Now, I don't have the reference here, but there was a presentation 2017 at Black Hat that covered embedded multimedia controllers and doing a lot of stuff with them. And they actually talk about building a device to be able to do this. So you can build it yourself. I actually bought my own, and it's you can get one of these EMCC Pros. It's like 140 bucks, but it comes with a device called a booster. And the booster allows you to do dead bugging, but it also allows you to do directly in circuit. So literally, I connect, once I've mapped out these things, I connect the data line, the command, and the clock line, and ground. And then one other thing you need to do is the primary processor. You need to find the reset for the primary processor, or in this case, it happened to be soft reset. The chip had a soft reset. And I was able to take the soft reset to ground, take the primary processor into reset mode so that it didn't try to engage the embedded multimedia controller. And then I was able to connect it up to my Ubuntu laptop and mount the file system up completely. At that point, you can do the DD and all that stuff straight up on the board and make modifications straight up. Of course, you have to map out these various connections to be able to do that. So, hopefully you guys liked this presentation and got something useful out of it. That pretty much concludes it. If you want to catch me afterwards and see the in-circuit connections to this, I may try to find a table with a power supply and hook it up so you can see this. Look at the board yourself and see what I did, how I hooked it up, and the device I used. The EMCC booster, like I said, you can go out and build these devices yourself, fairly cheap. This one you can buy off some Chinese site for like 39 bucks if you want to. The booster device, and it makes for being able to connect right into these devices easy. So, thank you very much. We got 5 minutes. Anyone have any questions? Yes, sir.
That last bit that you did, is that JTAG or is that something similar?
Well, this very last part, no, it's ISP, in-circuit programming. And it's common connectivity for embedded multimedia controllers. They all have that capability. Any other questions? Yes, sir.
If you're dealing with encryption circuits with utilities, and if you pull the key from memory, you have the key, and then you work with encrypting is there utilities?
Yeah, I probably don't have an answer to that. I have not. Yeah. I have not run across too many devices like that. I've dealt with Androids, which have Android devices which have that. The best source